Hey everybody, we are back. It's lesson 3.0 in the 2024 STEMNetX Data Science Coding Workshop. Welcome back. So I mentioned in the previous lesson, or maybe it was previous lesson, that we're going to be making the switch now from basic syntax and basic kind of programming techniques to more of applications that we see in the physical or quantitative sciences or numerical sciences maybe. The thing that I want to talk about today, or in this lesson, is one of my favorite techniques, and it's a different kind of way of approaching problems in, in the sciences. It's the idea of Monte Carlo simulation. So there are a few examples here of Monte Carlo techniques. Some of these earlier examples give an explanation of what Monte Carlo is, and then others are just kind of straight up applications. Then there are two examples here that aren't really Monte Carlo analyses, but they borrow basically the same ideas from some ideas from Monte Carlo. So you can check these out at your leisure or in your downtime. Okay, so I'll skip this joke, this little section here. What is Monte Carlo? Monte Carlo is a famous city. It's a city, I guess, but there are a lot of casinos there in the country of Monaco. It's very fancy. It's been in Bond films. When you think fancy casino from a Bond film, you're thinking about Monte Carlo. The actual Monte Carlo that we're talking about is a way of approaching analysis of systems that are either way too complicated to actually make concrete, definitive predictions about, or the systems have some baked-in probabilistic nature where there isn't a way to make a definite prediction about them. So you can read this little blurb from Wikipedia here. The basic idea of a Monte Carlo analysis is that we take some system. So let's say it could be, a common example is like take a system of all of the teams in Major League Baseball for a season. We want to make a prediction about how likely is it that the Pittsburgh Pirates will win the World Series. It's not very likely. But what we could do is we could model their playing of the season based on some statistical outcomes of individual games, or we could even model it at the player level. When I say model, what I mean is we would be generating randomly the outcomes of individual plays or the outcomes of games, and then putting together all of those random predictions to produce some type of estimate at the end of this Monte Carlo analysis of the probability that they will win. And the way that we do this, the term for this is we are sampling the events from some distribution. We're sampling them randomly from some distribution. We're going to do two very concrete examples in this notebook, and then we'll have some homework problems at the end of the notebook. I'll probably code up the solution to one of the homework problems, but you'll get an idea of how this process works. So yeah, definitely read this section. It'll give you a better idea of what we're after here. Pretty much any time an instructor introduces the idea of the Monte Carlo method, MC method, to a group of students, we start with this basic, it's kind of the canonical example, the de rigueur example of calculating pi using the Monte Carlo method. Now, if you've taken a calculus class, probably Calc 2, you know that there are a bunch of like series expansions or series expressions, infinite series expressions that are related to pi. Pi itself is a really fascinating number. You could explain what pi is to maybe like a second or a third grader. If you have a circle and you measure the circumference of the circle and the diameter of the circle, and you divide the circumference by the diameter, you will get the number pi no matter what circle you're talking about, as long as it's a perfect circle. Pi itself as a value is a transcendental number, meaning it's not the root to any polynomial equation, which for our purposes means it's very difficult to calculate. You can't just write down, pi equals 3. You have to have some infinite series expansion that you may have seen in Calculus 2 or somewhere like that. So I don't know why I'm giving you a thumbs up right now. I didn't really. Why not? Let's do it. Okay, there we go. So let's imagine that we don't know any of those really fancy infinite series expansions for pi. One way that we could estimate a value for pi is by doing a random sampling. So you can read this section here. It's going to talk about the basics of this analysis. I'm just going to scroll down to a visualization of what I'm talking about here. So this chunk of code, this code cell, is really all just set up to make this visualization. So we have a graph, You can think of this as maybe being a circular dartboard. The circle, which is the shaded region in this graph, has unit radius, so it has a radius of 1. That means that the area of that circle would be pi times the radius squared. 1 is the radius, or the radius is 1, so pi times 1 squared is just equal to pi. The area of this circle is equal to pi. The area of the square that it lives in is, well, let's see, it's 2 units on the bottom side, on the horizontal side, and it's 2 units on the vertical side. So its area is 2 squared, or 4. So we have 2 different regions here. The circle, which has area pi, let's assume that we don't know the value of pi for right now, lives within the area of the square, which we know has an area of 4. So the way that we are going to Monte Carlo evaluate the value for pi is we are going to randomly generate a whole bunch of xy points within this square area. So if we do that over and over and over again, let's say we do it 1,000 times, we count up the number of those points that fell within the circle. The number that fell in the circle should be proportional to the area of the circle, and the number that fell in the square is kind of like our normalizing area, so all of them certainly fell within a square. So the ratio of the area of the circle to the area of the square should be proportional to the ratio of the number of points that fell within the circle to the number of points that fell within the square, or the total number of points generated. You can imagine, we're going to do this with a computer, obviously, but you can imagine doing this with a dartboard and just a whole bunch of darts. As long as you're really good at randomly throwing darts within a square area, you could set this up in, not in a dorm room, hopefully, because you don't own the wall there, but you could imagine just kind of like randomly throwing darts at a board, or maybe even drawing this on the ground where you have a very close to perfect circle, and you have a square in which that circle is embedded or circumscribed, and then you just kind of like throw pebbles onto the area, or you flip coins onto it or something like that. You count up the number of random throws that were inside the circle, and you divide by the total number of throws. So this is what we're going to do. Now, the basic techniques we already have. We know how to generate random numbers, but we are now using that random number generation in the service of actually estimating the value of some very important quantity, namely pi. So let's just get to it. So what are we going to do? All right, well, I guess we don't have to get to it because the code has already been written for us. We're going to adapt this code later on. So we have some variable declarations here. The radius of our circle is equal to 1. This variable n is 10,000, or sorry, 100,000. 1 times 10 to the 5. That's just the total number of dart throws we're going to make, or the total number of points in 2D, in the 2D plane that we're going to make. N samples, this is just going to count up the number of times we've thrown the dart so far, or number of points we've generated so far. You see we have a while loop below. And NC, this is going to be a counter variable which just increments every time we find another one of our points to be within the circular area. So these two lists right here we're going to use just for visualization purposes. You can ignore those right now. Now you can see what's going to happen. We have a loop. We're going to generate a whole bunch of random points. And the way the loop is going to work is we're just going to count up the number of samples. Every time we generate a new point, we would say that we are sampling the region, sampling the area. And we're going to keep doing that as long as samples, or n samples, is less than n. N is, again, the total number of samples we're going to make. We're going to generate 2 random ordinates, or a pair of coordinates in the 2D plane. Each one of these values is going to fall between -1 and 1. So we're going to have an x value between -1 and 1, and we're going to have a y value between -1 and 1. That's going to be our point in 2D space. So these are just our random point generation right here. Once we generate that point, we increment the number n samples. Okay, fine. Then this little conditional is just going to check whether the number we generated is within the circular region. So how do we do that? We square the x value, we square the y value, and then we check to see if the sum of those squares is less than the square of the radius. The equation that defines the perimeter, or the circular shape, is x squared plus y squared is equal to the radius squared. So if x squared plus y squared is less than the radius squared, the point we generated falls within the circle. If that's the case, if the point is within the circle, we're going to increment NC, the number of points inside the circle, by 1. Then, I guess every step through this loop, we're going to approximate the value of pi, and we'll do that by taking 4 times NC divided by n samples. There's a factor of 4 in there. You can read about why above. There's an explanation of where that comes from. Then we have a couple different conditionals here. If the number of samples is divisible by 1,000, so n samples percent 1,000 equals 0, just checks to see whether the number that we've generated so far is divisible by 1,000. If it's a multiple of 1,000, we're going to print out after the number of samples. Our approximation of pi is our approximation of pi value. This funky piece of syntax right here, this is the Unicode code for the symbol pi. You'll see we'll actually print out pi to our output. The symbol pi looks pretty cool. And then same type of thing, if the number of samples is divisible by 1,000, we're going to append our approximate value of pi and our number of samples to the 2 lists that we created above. That's just so we can plot the value of pi, or our approximation of pi, as a function of the number of samples. So I'll go ahead and run this code. Hopefully it's going to work. Hey, check that out. So after 1,000 samples, our approximation of pi is 3.112. That's not so great. It gets worse for a little bit. So it then goes down to 3.08. You probably know that pi is approximately equal to 3.141, and then, infinitely many more non-repeating digits after that. And then as we generate more and more samples, our number becomes a better and better approximation of pi. It wiggles around. It's not always getting better because this is a random process. You can see that if I scroll down here, after 100,000 samples, our approximation of pi is 3.12992. So depending on what your definition of good is, that might be not good enough for the calculation you need. But the technique is very powerful here. We've not used calculus. We've not done any kind of fancy infinite series. We've not appealed to string theory or anything crazy like that. We're just making a very simple random sampling of the plane, and we're able to approximate the value of pi. This graph is like a nice time series graph of our approximation of pi as a function of the number of samples we have. So it starts off not great, it gets even worse, and then it kind of slowly creeps up here closer and closer to 3.14. Let's run this chunk of code again, and I'm going to turn down the amount of reporting we get. So rather than every 1,000 samples, I'm going to turn it up to every 10,000 samples so that we get a, whoops, I didn't want to do both of those. I'll still get the same graph, but I want less reporting. Okay, great. So check this one out. So by the end of the simulation, after 100,000 samples, our approximation of pi is 3.14232. So that is closer than our previous. And you can see that, again, because this is a randomized process, our initial approximation this time was way too large. It was larger than pi. And then as the number of samples increased, it approached pi. Let's just run this 1 or 2 more times and see if we get any interesting behavior. So again, here it starts lower, and then it seems to settle down, 3.1442, kind of interesting. Let's run this again. In this case, again, we started lower, 3.09, and it approached 3.1448 eventually after 100,000 samples. What if we turn it up to 1,000,000 samples, just for the heck of it? Let's see how this works. So in order to do that, I would just need to turn the n variable in my code up to 1 times 10 to the 6. Run this thing, seems to be getting, okay, check this out. So in this case, after 1,000,000 samples, our value of pi, and again, this is just approximation from randomly sampling the plane. Our approximation of pi is 3.141404, not too shabby. And you can see that while the value starts off no dang good, so initially it's almost 3.17, that's not close, and it dips down to 3.11, after many, many iterations, our approximation stabilizes. Should we try 10 million? Let's try 10 million just for the heck of it. Computing power is cheap, at least at my house. All right, so let's turn our reporting to the output here up to every 100,000 and we will turn this up to 10 million. And you know what, we don't need that many data points, so I'm going to turn that up to 10,000. Okay, so it's chugging, it's chugging, it's chugging, it's chugging. Oof, can't keep up, I can't keep up. Hey, there we go. All right, so after 10 million samples, our approximation of pi is 3.141946. And again, you can see while initially we had a lot of jitter, there was statistical uncertainty just because this is a random sampling process. After many, many samples, this thing kind of stabilizes to a value close to pi. So again, take a step back. What is Monte Carlo in this context? We want to know the value of some number. We can't directly calculate that number. So what we've done is we've generated a random sampling of some system. In this case, it's like random points in 2D. Are they inside the circle or are they not inside the circle? And we use that random sampling, many, many random samples, in order to approximate the value we're after. Again, that's the whole idea of a Monte Carlo system or a Monte Carlo approach. All right, let's do a warm-up problem. We'll adapt this approach. So tinker with the code above to determine, I don't want to do that warm-up problem, sorry. That has to do with approximating pi again. Let's do a live demo. Okay, so totally different from a warm-up problem, right? So in this live demo, I'm going to use the Monte Carlo method to approximate the area under the function sine of theta between theta equals 0 and theta equals pi. Pretend we don't know what an integral is. So let's assume some like counterfactual universe where calculus hasn't been invented yet. However, we all have laptop computers. I don't know how that could have actually happened, right? But it's, I guess, an interesting science fiction concept. So we don't know how to do an integral, but we do know how to randomly generate a whole bunch of points in the 2D space. Here I've graphed sine of theta as a function of theta, and you can probably guess what we're going to do here is we're going to randomly generate a whole bunch of points that fall within x between 0 and pi and y between 0 and 1. So those points fall in the rectangle from here to here and then from here up to there. And we're going to just check whether those points are under the function sine of theta. So let's do that. I'm going to, just to show you how the pros do it here, I'm just going to steal a whole bunch of the code from above. Okay, so I'm going to grab all of this stuff and just paste it down here. Some of it we'll use, some of it we'll modify. Okay, and let's go through here. So for the time being, let's just start with 100,000 samples, and I'm going to change this thing to be n sine, meaning the number of points that fell under the sine function. Okay, I'll do this as sine int values for the values of the integral of sine. And then while n samples is less than n, that still works. This is just my general while loop structure. Now this one I have to change. So np.random.rand, here I'm using the numerical Python random library, which is a little bit from the kind of more built-in Python library that we used in previous lessons. It does the same thing. This np.random.rand generates a random number between 0 and 1. For the x value, we don't want that random number to be between 0 and 1. We want it to be between 0 and pi. So there are a couple different ways I could do that. One is I could just use a good enough 3.14159. That's good enough for me value of pi. So if I multiply that by a random number between 0 and 1, I'm going to get a random x value between 0 and pi. Works for me. And then the y value, as I mentioned before, we want it to range between 0 and 1. So when we do that, we're going to be generating a random xy point where x is between 0 and pi and y is between 0 and 1. All right, then we want to check whether that random xy point is below that sine function. So the way that we do that is we do this. If y is less than, we want to take the sine of the x value. And I'll change my comment here. Check whether point is below the sine function. Now, I know you're probably going to be griping because above I defined the problem in terms of theta. Here I'm just using x. Okay, fine, I'll change it. So we'll call this theta, and I'll call this theta here. That should work. So I have theta and y. Okay, great. If y is less than the sine of theta, I'm going to increment n sine. That sounds good. I have my approximate sine int. This is simply going to be equal to nc divided by n samples. Let's think for a minute if that's the case. So this would be the fraction of nc divided by n samples would be the fraction of the total area that's gobbled up by that sine function. I want to multiply this by the total area. So that's going to be equal to pi times 1, because the rectangle is pi on one side, times 1 on the other side. So I'll just multiply this by our value of pi. N samples, yeah, looking good. After n samples, our approximation of the area is approx sine int, for approximation of the integral of sine. And let's see, yeah, this looks good. So I just want to change some of the variable names here. So sine int vals, approx sine int, and then n vals, n samples. Okay, this is looking good. Then I just need to change the plotting code down here. That's going to make our graph for us. N vals is fine. Pi vals, I didn't call this pi vals. I called it what? Sine int vals. That's the list of values of our approximation. X label, yeah, that looks good. I'm just going to make this thing sine of theta. Now, the syntax that I'm using in here, so $sign / sine paren / theta, that's LaTeX code. If you've used LaTeX in the past, great. If not, also great. Don't worry about it. This is just going to render some nice mathematical notation for us if I've done it correctly. So let's run this and let's see what happens. I'm going to turn the reporting, make the reporting more frequent here. Okay, so something is not going right. So you may know that the approximate value of the integral of the sine of theta is nowhere even close to 246. So something wacky is happening here. Let's see if we can figure it out obviously. If not, let's see if I made an obvious mistake. If not, we'll pause and we will go, I'll fix it offline and then come back to you and tell you about the mistake I made. So let's see, this is embarrassing, but I think I can rebound. That's looking good, so theta is looking good. So theta is going to be some value between 0 and pi. Y is going to be a value between 0 and 1. I increment the number of samples. That looks good. Yes. So. Oh, all right. So it's not NC here. It's N sine. Let's see if that solved our problem. That NC variable that I had right here was from the previous example. Yikes. See, this is the danger of a live demo. It's not really live, but I like to pretend that it is live. Okay. All right. Is that looking correct? So the integral of sine from 0 to theta. Hold on. I'm going to pause for 1 minute. I'm going to do this integral analytically, and then I'm going to come back and we'll check our answer. Stick with me. Hey y'all, I'm back. I figured out the problem. The problem is not the programming here, not the Monte Carlo analysis. It's that I've forgotten how to do calculus 1. So when I evaluated my integral analytically, I did the limits of integration incorrectly. So that's embarrassing, but the good news, this is not a Calc 1 workshop. This is a computational science workshop. So we're in good shape. So the integral we're looking for, the value that we're looking for is 2. I actually, in trying to debug this, printed out a whole bunch of stuff. You can ignore that line. But this cell of code here does give a correct Monte Carlo analysis to find the area under sine of x, sine of theta between theta equals 0 and theta equals pi. Let's run it again, and we see that this thing approaches 2. Let's take a look at the graph. So this particular sampling, this particular run of the of the code here starts way above 2, and then it eventually settles down to approximately 2. Something got goofed up with my axis label here. Let's see if I can correct that. Yeah, I'll just get rid of this. This was perhaps a bit too fancy for this application. So let's do that. Looking good. All right, let's scroll down and take a look at our graph here. So again, the approximation of this integral started way high, 2.03. It dipped way low, 1.98, 1.97, something like that. And it eventually approached 2. Now again, this is an approximation technique. We're assuming that sine of theta, for theta equals from 0 up to theta equals pi, is just too complicated for us to do by hand. That turned out to be true for at least one person in this video, but I eventually outsmarted myself, so we got there. Now this is just a, this is just kind of a goofy Mickey Mousey demo problem. Normally the types of problems that we apply the Monte Carlo technique to are really, really difficult to grind out kind of a closed form analytical answer to. So I'll give you some examples of those things below. Now, this section of this notebook you can read on your own. This is an example of how we might use the Monte Carlo sampling technique to model something like Dungeons and Dragons style turn-based role-playing game. If you're into that type of thing, go for it. You can dig into this example. You might go way down the rabbit hole on this example. I'll let you read that if you're interested. It gets pretty long, but you'll see how the same type of approach of randomly sampling the possible outcomes of an individual turn or an individual battle, and then putting together the outcomes of many, many simulations of those battles can allow us to approximate the probabilities of certain things happening in that battle. Let's move on to some homework problems. So I would recommend definitely reading through that Dungeons and Dragons style problem. But this might give you a better idea of the types of things that we apply Monte Carlo analysis to. So here's a very simply stated problem. Perform a Monte Carlo analysis. We'll do number 1, B days. Perform a Monte Carlo analysis to estimate the probability that in a group of 20 people, at least 2 people share a birthday. So this is a common kind of party trick if you're at a party with 20 or more people. Now, at first blush or at first glance, it seems like the probability would be small, right? Because there are 365 days in a year. The probability that any 2 people share a birthday, I mean, what are the odds? There are just so many different days on which 2 people could be born. But we're going to show that that's actually not the case using this Monte Carlo technique. Now, usually when we code up a Monte Carlo analysis, we do it in steps. So we're going to generate kind of one random set of people at a party, one set of 20 people at a party and their birthdays. And then once we have that working, we're going to put that single party guest list into a loop and do it many, many times to approximate the probability in general that any 2 people share a birthday. All right, so I think the first thing that I want to do is let's generate the birthday. So I'm going to create a new list that I'm just going to call B-Day list. It's going to be empty. And then for I in range 20, because I want to generate 20 random birthdays, I'm going to do np.random.randint, and I'm going to generate a random integer between 0 and 366. Now it excludes 366. Or I guess I want to do 0 and 365. This is going to generate a random integer for me that's between 0 inclusive and 365 exclusive. That random number is just going to indicate the day of the year that each of these people is born on. And what I'm going to do with that value is I'm just going to append it to bday list. Append. Okay, great. And after I've done that 20 times, I should have a list of the birthdays. So bday list, birthdays of the people at my party. And there they are. So the first person was born on the 174th day of the year. The second person was almost at the tail end of the year, the 362nd day, 256th day, so on and so forth. Note that if I run this block of code again, I get a completely different set of party goers. Whoops, I went down too far. Run it again. Because this is a random sampling process, That works over and over again. All right, the next thing I have to do is I have to check whether there are any repeats in this list. Now, there are a whole bunch of kind of brute force ways to do that. I'm going to show you how to figure out how to do this in a sophisticated way. So the first thing that I'm going to do is I'm going to print, let's do this. So let's print out the length of this list. So print len of bday list. You guess right now what it should be. So we know what it should be. It's 20. So there are 20 numbers in this list because I appended 20 numbers to this list. And I should have also said, before we started coding up this analysis, guess in your head what you think the probability that any two people share a birthday out of this group of 20, randomly sampled group of 20. And see if you're surprised by the final answer that we get. All right, now, I have a list of 20 birthday day numbers. If I were to take this list and remove all of the repeats, the repeated numbers, I would wind up with a list that only has the unique birthdays among these 20 people. If I do that process, and so I remove all the repeats, and I get back a list that's still 20 elements long, that means that there were 0 repeats, and that means that no two people shared a birthday. If I get back a list that's shorter than 20, that means that at least one of the birthdays was repeated, at least two people shared a birthday, and that's exactly the thing that we want to investigate. So I'm going to get a new browser tab here, and I am going to Google Python remove duplicates from list. Oh my gosh, look at this. Look at this open source community. Somebody has already Googled this probably hundreds of millions of times. Let's go to Stack Overflow. Removing duplicates from list. That sounds like, how can I check if a list has any duplicates and return a new list without duplicates? Oh my gosh, that's exactly what we're trying to do. Thank you, Carl Nechtel, on October 11th, 2022. Okay, so let's see. Okay, I don't necessarily want that. So the common approach to get a unique collection of items is to use a set. Sets are unordered collections of distinct objects. To create a set from any iterable, meaning a list, you can simply pass it to the built-in set function. So it sounds almost like a cast. Okay. Ooh, that's really complicated. I don't like this first response. This might be the most elegant way to do it, but holy cow, I got to know a lot of stuff in order to pull that off. Let's scroll down to the next. Okay. Oh my gosh, this person is having me import a new ordered dictionary, and that's in Python 2.7. We're not using Python 2.7. Okay. Oh my gosh, another person using set? Holy cow. Okay, so I'm going to go out on a limb here. It looks like we can cast this list to a set. So this person is like defining a function which basically just converts a list to a set and then back to a list. So let's try something like that. Let's check a couple more answers. Oh my gosh, look at this. I don't even know what that means. Okay. Okay, here's a unique thing. Okay, so let's do this. Okay, here's a numerical Python solution using a numpy function unique. So we would import numpy as np, that's great. And then we would use this unique function which seems to take a list, and then we would convert that thing back to a list. So let's just check this now. All right, so I'll call this unique list. That will be equal to numpy.unique, and I'm going to use our bday list to that thing. And then this guy makes the unique list out of that thing and then converts it back to a list. And then maybe we don't even need that, so I'm just going to do this. So print len of unique list. Okay, great. All right, so this is at least spitting out a number. Let's run it a bunch of times. So in this case, here are our birthdays. Just glancing at this, I don't see any repeats, but that's not an airtight analysis there. But it's looking like our original list has 20 elements in it, and our unique list, which should remove all of the repeats, also has 20 elements. Let's run this a couple more times. Okay, so there we have a repeat. Let's see if we can glance at this and figure out what it is. Oh, here it is. So 223, 223, and 223. Whoops, 220. Whoops. Oh my goodness. 223 right there. So there is one repeat in this list. There is one shared birthday. And when I called numpy.unique on that list, it got rid of that repeated. Let's see if we can run this a few more times. So one repeat again. 2 repeats in that case. So it removed 2 repeats and we wound up with 18. Okay, great. All right, so this is looking good. We know how to check whether there are uniques in this list. So I'm just going to get rid of some of this printout stuff. Okay, great. And now what I'm going to do is I'm going to put this in a while loop and actually generate a whole bunch of party guest lists. So like this code right here generates the one single group of 20 people. I'm going to do that over and over and over again and just see if I can count up the number of times that we get a repeat. So what I'll do is I'll have n parties. Let's do 100,000 parties. So 1 times 10 to the 5. We'll say n matches is equal to 0. We're going to start at 0 like that. And n samples is equal to 0. And we'll do while n samples is less than n parties. Okay, great. And then all of this stuff that generated one single party, one single set of party guests or guest list, I'm going to put inside a loop. I'm just going to do it over and over and over again. Then what I'm going to do is I'm going to check if the length of the B-Day list is equal to, or no, I want to check and see if it's not equal to the length of, and I'll just come down here and grab this stuff. So actually, maybe I should compute unique list first. Yeah, let's do this. So I'll compute the unique guest list. And then I will compute the length of unique list like that. If those two things are not equal, then we have a number, we're going to increment number of matched birthdays, n matches by 1 is equal to n matches, matches plus 1. Okay. And at the end of this process, what we want to do is we'll print out the approximate probability of at least one match birthday is, and then I will print out n matches, I did it again, matches divided by n parties, or n samples would work too, that's fine, because n samples is going to go up to n parties, and then our loop will exit. Now, this is not going to work, okay? I know that this is not going to work. If I press Shift-Enter right now, my computer will enter into a while loop that will never end. And the reason for that is I haven't incremented n samples. So every time through this loop, I'm doing a new sample. I want to increment that counter variable. So I'm going to say n samples is equal to n samples plus 1. And I should also say that there is a more compact syntax for doing this incrementing thing. So this is like a syntax that we've used a whole bunch of times. I'm adding 1 to n samples and then just resetting the value of n samples to be that new 1 greater value. There's a very compact syntax that does that. So it's just n samples plus equals 1. That just means, hey, add 1 to the previous value and store it in the variable. I could have used that same thing up here. Well, I'll leave it the way it is. All right, I think that this is not going to enter into an infinite loop that reduces my computer to a puddle of molten silicon. Let's see what happens here. So I'll run this. All right, we got an error. Name n samples is not defined. N samples. Where is that? Oh, yeah, I typed that wrong. N samples. Where is that? Oops, there it is. N samples. All right, let's run this again. Now, that suspiciously took longer to run than our previous examples where we were approximating the value of pi or approximating the area under sine of theta. And I am a little bit freaked out by that at first, but actually I think it's okay. And the reason for that is 100,000 times we generated 20 numbers and then did some operations on those numbers. So in the case of the approximation of pi above, each time through our while loop, we really only had to do one or kind of two things. We generated a single point in 2D space and then did an operation on that thing, checked to see if it was inside a circle. Here we're actually doing like, I don't know, 20 times 10 to the 5 because we're doing 20 numbers in each of 10 to the 5 samples. That's a lot of computing, so it's not shocking that this thing took a moment longer to run. If I turn this up to 1,000,000, so what value are we getting here? The approximate probability is 0.41176 or 41.2%. That's a lot higher than you maybe would have assumed. I should mention that this is a problem that you can solve analytically with some semi-sophisticated probability type stuff. We're not going to do that. We've done this with the Monte Carlo approach. Let's turn this up to 1,000,000 samples and see if we get something similar. So I'll run that again. It's going to take longer to chug through this. Actually, you know what? I'm going to stop this and give us some reporting here. So I will say if n samples percent 1,000 is equal to 0, we'll just print out n samples. Just as a sanity check, just to say, okay, this thing is still running. Our computer hasn't died on us, hasn't frozen up on us. Okay, so there we go, there we go, there we go. Oops, it put it in a scroll down. Okay, great. Wow, that's a lot of samples. Holy cow. Who asked Python to do that many samples? All right, it's still running on my machine. Is it done yet? This is pretty cool the first time you program a computer to do a calculation that takes longer than instantly. I think so. All right, it's telling us our approximate probability of at least one matched birthday is 41.16%. That's fine. Now, if you're a gambling person, you could maybe make some money on something like this. So let's turn this back down to 100,000. Let's say you're at a party with not 20 people, but 30 people. What do you think the probability is that at least two people share a birthday in a group of 30 people? Someone who hasn't done the Monte Carlo analysis or hasn't taken a good prob stats course and hasn't done this problem before might assume, well, 30 people and 365 days in a year, that's got to be really unlikely. And then you, wanting to make some money, could say, let's put a $5 on it. Let's put $5 on that. I bet you at least two people in this room share a birthday. Okay. In this case, whoops, we're still going. For 30 people, the chance that two people in that room, randomly generated or random sampling of birthdays, share a birthday is 0.705 or 70.5%. That's a pretty good bet if you want to make $5. It's not going to come through every time. It'll come through 70% of the time. Now, I should say that this is a very simple model of how birthdays, it's assuming that birthdays are randomly distributed throughout the year. You might know that birth dates are not randomly distributed throughout the year. There are more babies born in certain seasons and things like that. That gets into a whole human nature thing, which is outside the scope of this workshop. But this is a good first approximation to simulating a system like this using the Monte Carlo approach. Hope you enjoyed it. Students usually really like Monte Carlo. It's a cool idea. It opens the door to some fun types of programming and analyses. I'll see you in the next lesson. Thank you.